Hi all. ഇന്ന് നമ്മൾ ഡിസ്കസ് ചെയ്യുന്നത് കൺവെർജൻസ് നോഷൻ ഓഫ് ഫോറിയർ സീരീസ് ആണ്. അതിനു മുന്നേ ആദ്യമേ നമ്മൾ തിയറം 8.11 പ്രൂവ് ചെയ്യും. 8.11 പറഞ്ഞിരിക്കുന്നത് സപ്പോസ് വി ഹാവ് സീക്വൻസ് ഓഫ് orthonormal system of functions that is phi n and we replaced the closed interval minus pi and pi by this ab. Now we define Sn of x. Sn of x is the sequence of partial sums of the Fourier series of f corresponding to this phi m, that is the nth partial sum. And suppose Tn of x. Tn of x is a partial sum of some series. This need not be the Fourier coefficients. This is arbitrary coefficients. Okay. Now you can get this inequality. Integral a to b mod f minus Sn whole square dx less than or equal to integral a to b mod f minus Tn whole square dx. Okay. ഇതിൻ്റെ മീനിങ് അല്ലെങ്കിൽ ജോമെട്രിക്കൽ മീനിങ് എന്താണെങ്കിൽ അല്ലെങ്കിൽ ഇതിൻ്റെ ഒരു എന്താ പറയുക അണ്ടർലൈൻ മീനിങ് എന്താണെന്ന് വെച്ചാൽ നിങ്ങൾ തുടക്കത്തിൽ തന്നെ ഒരു ഇന്നർ പ്രോഡക്റ്റിനെ പറ്റി കേട്ടിട്ടുണ്ടാവും ഫങ്ഷണാലിറ്റി ക്ലാസ്സിൽ. ഇന്നർ പ്രോഡക്റ്റ് എഫ് ജി എൽ പി സ്പേസിൽ ഡിഫൈൻ ചെയ്യുന്ന ഇന്നർ പ്രോഡക്റ്റ് ആണ്. ദിസ് ഇസ് ഇൻ്റഗ്രൽ എ ടു ബി എഫ് ജി ബാർ ഡി എക്സ് ഓർ ഡി ടി. ഓക്കെ, ഇതിനെപ്പറ്റി നിങ്ങൾ കേട്ടിട്ടുണ്ടാവും. This is the inner product, and corresponding to this inner product you can get a norm. Norm f square is integral a to b f conjugate dx, that is mod f square dx. So this is the norm. This norm induces a distance in that space. Dfg is equal to norm f minus g. This will be a distance, and as far as we consider this distance, we can give a meaning for this inequality. Okay, so the distance between f and g is defined as using this definition integral a to b mod f minus g square dx. ഇതാണ് ഡിസ്റ്റൻസ് എന്ന് പറയുന്നത്. എഫ് ജി തമ്മിൽ ഡിസ്റ്റൻസ് എന്നാണ്. ഈ ഇൻഇക്വാലിറ്റി കൊണ്ട് നമ്മൾ മനസ്സിലാക്കേണ്ടത് എഫും എസ് എനും തമ്മിലുള്ള ഡിസ്റ്റൻസ്. ദിസ് ഇസ് ഇഫ് യു ടേക്ക് ദിസ് ഇസ് in fact norm is whole ratio 1/2, so we have to write this as this whole ratio. This norm f square is this one, so norm is whole ratio 1/2. So when you take the 1/2 power of this inequality, raising the power 1/2 on both sides, you will get norm f minus Sn is less than or equal to norm f minus Tn. Sn എന്ന് വെച്ചാൽ sequence of partial sum of Fourier series. ഇത് sequence of partial sum of ആർബിട്രറി സീരീസ് എന്ന് വെച്ചാൽ ആർബിട്രറി കോഎഫിഷ്യൻസ് ഉപയോഗിച്ച് എഴുതിയിരിക്കുന്ന സീക്വൻസ് ഓഫ് പാർഷ്യൽ സം ആണ്. അപ്പോൾ ഈ പറഞ്ഞ ടി എൻ ഓഫ് എക്സ് ഇങ്ങനെയുള്ള ആർബിട്രറി പാർഷ്യൽ സംസുകൾ എടുത്തു കഴിഞ്ഞാൽ അതിൽ എഫിനോട് ഏറ്റവും അടുത്ത് കിടക്കുന്നത് അല്ലെങ്കിൽ എഫുമായിട്ട് ഏറ്റവും അപ്രോക്സിമേഷൻ വരുന്നത് ഫൂറിയർ കോഎഫിഷ്യൻറ്റിനാണ് അല്ലെങ്കിൽ ഫൂറിയർ കോഎഫിഷ്യൻസ് ഉപയോഗിച്ചിട്ടുള്ള സീക്വൻസ് ഓഫ് പാർഷ്യൽ സമ്മിനാണ് എന്നാണ് നമ്മൾ ഇതിൽ നിന്ന് മനസ്സിലാക്കേണ്ടത്. അപ്പോൾ വെറുതെ ഒരു ഇൻഇക്വാലിറ്റി പ്രൂവ് ചെയ്യുന്നതല്ല, ഇതിന് അതിൻ്റെതായ മീനിങ് ഉണ്ടെന്നുള്ളതാണ് നമ്മൾ മനസ്സിലാക്കേണ്ടത്. ഓക്കെ, നൗ വി ക്യാൻ പ്രൂവ് ദിസ് തിയറം. തൽക്കാലം പ്രൂവ് ചെയ്യാനായിട്ട് നമ്മൾ ഉപയോഗിക്കുന്ന ഇൻ്റഗ്രൽ എ ടു ബി എന്നുള്ളതാണ്. സോ വി വിൽ യൂസ് ഇൻ്റഗ്രൽ ഫോർ ദിസ് integral a to b. നമ്മൾ ഈ നൊട്ടേഷൻ ഇൻ്റഗ്രൽ മാത്രമേ ഉള്ളൂ. ഇറ്റ് ഈസ് അണ്ടർസ്റ്റുഡ് ദാറ്റ് ദ ക്ലോസ്ഡ് ഇൻ്റർവൽ ഇസ് എ ബി, സോ വി നീഡ് നോട്ട് വറി അബൌട്ട് ദി ലിമിറ്റ്സ്. Similarly, if you write summation m equal to 1 to n, we write instead of this we write summation. Okay, summation cm etc. So that will denote this summation m equal to 1 to n, because it contains only a finite terms of the summation. So we use these two notations. So we evaluate, our intention is to prove this inequality. So first we evaluate integral f t n conjugate. What is integral f? That means integral a to b f of t f of x t n of x dx. Okay, t n x conjugate dx. Then evaluating this will be same as f times, you can substitute for this t n conjugate. T n conjugate is conjugate of these summations. It contains n terms, so you can take the conjugate of this, so that will give summation gamma m conjugate phi m conjugate. since it contains a finite number of terms, you can interchange that summation and integral, that is summation integral gamma m f times gamma f times gamma m conjugate phi m conjugate, and since this gamma m is independent of this integral, so we can take it out from this integral, then that will become summation gamma m conjugate integral f phi m conjugate. Okay, so this will give our Cm. So we write this as summation, this is same as summation gamma m conjugate, this is our Cm. Okay, this is because of the definition of Cm. The integral f phi m conjugate is nothing but the Fourier coefficient. Now you evaluate integral mod Tn square, that is integral Tn conjugate. So that will give integral Tn as summation gamma m phi m, and Tn conjugate is written as gamma k conjugate phi k conjugate. This can be written as since this is summation n equal to m equal to 1 to n, and this is summation k equal to 1 to m. So when you multiply these two terms, then you will get integral summation where double summation over m comma k. M is m from 1 to that n, and k is from 1 to n. We have gamma m gamma k conjugate phi m phi k conjugate. So this is the product of these two. It contains only finite number of terms, so you if you take the term by term multiplication, you can get this one. Okay, but we know that this contains only a finite number of terms, so you can distribute this integral to the inside, then that will give summation m comma k integral this gamma m and this gamma k conjugate are constants, so you can take out this gamma k conjugate. Those two quantities are independent of x, then gamma m and gamma k conjugate can be taken out from this integral, then remaining will be phi m phi k conjugate. Okay, so we know that as m and k varies, this integral survives only when if these two suffixes are the same. Okay, otherwise since this phi of n form a orthonormal system, this integral will be 0 if m not equal to k. So if m equal to k, this will be 1, and in at that the only surviving term from these two summations, this double summation is the term corresponding to m equal to k. So at that time gamma m conjugate will be the only term, so that will give gamma m. This will be summation gamma m square. That means when you expand the first inner summation from k equal to 1 to n, then when k is equal to m, you can get the only surviving term. So that is summation m is equal to 1 to n gamma m square. The only surviving term is this. Okay, gamma m square, mod gamma m square. Now this is because of the orthonormal property of this system. Okay, now you evaluate integral modulus f minus tn square, that is equal to this is f minus tn into f minus tn whole conjugate, f minus tn into f conjugate minus tn conjugate, that is conjugate of this term. So this will give integral mod f square minus integral f tn conjugate minus integral f conjugate tn, and finally we have integral mod tn square. Okay, so this is equal to integral mod f square minus, we have evaluated integral f tn conjugate. What is integral of Tn conjugate? That is same as summation gamma m conjugate Cm. Okay, and this will be the conjugate of this term. Conjugate of integral f Tn conjugate is integral of f conjugate Tn conjugate whole conjugate. Okay, so that will give the conjugate of we need to replace this by conjugate of this one, so that will be minus of summation Cm conjugate gamma m. Okay, and finally we have mod Tn square. Integral mod Tn square is equal to this summation gamma m conjugate, summation gamma m conjugate, that is mod gamma m square. So we write as it is gamma m conjugate. Okay, now this is equal to, we will replace this this whole quantity, this quantity by some other term. If we observe this, what is gamma m minus Cm whole square? This is summation gamma m minus Cm into gamma m conjugate minus Cm conjugate. Okay, so this will be summation mod gamma or gamma m conjugate. So this is the first term, and if you split the summation throughout this multiplication, then you will get the first term is gamma m conjugate, and the next term will be minus summation gamma m Cm conjugate, and the next term will be summation Cm into gamma m conjugate, and finally we have plus summation mod Cm square, that is Cm into Cm conjugate, that is Cm square. So we replace these two quantities. Okay, gamma these three quantities from this is the last three quantities are here. These are the last three quantities. Okay, so these three quantities can be replaced by this minus this one. Okay, so we can get this equality as summation mod f square, and these three quantities can be replaced by this minus summation mod Cm square. Okay, so that will be I will write the last term first, minus mod Cm square plus summation mod gamma m minus Cm whole square. Okay, so that is the value of this integral f minus Tn square. Okay, then this we need to minimize this distance. We need to prove that this distance, this is minimum if we replace Tn by Sn. Okay, so if we replace this then we need to that means we need to find out the minimum value of these quantity. Okay, mod f square minus gamma summation Cm square plus gamma m minus Cm square. Okay, so if you consider this term, then this gamma m is the only varying term is gamma m. Gamma m is the arbitrary coefficients. Okay, so when you change this gamma m, we need to replace this Tn by arbitrary sequence of partial sums. That means we need to replace this gamma m by arbitrary sequence. So these two quantities are fixed. F is given, then f and Cm are fixed. Okay, so you can minimize this right hand side by minimizing the last term. Okay, gamma m different values കൊടുത്താലാണ് നമുക്ക് ഇതിന്റെ minimum value കണ്ടെത്താൻ പറ്റുക. So we need to use the minimum value of this expression only if this gamma m is Cm. Okay, the minimum value of this summation, the last term, the minimum value of this last term is nothing but 0. Okay, so this can be minimum if and only if this gamma m is equal to Cm. Okay, so that is the meaning of that. So we can say that mod f minus Tn square will be minimum if we replace this gamma m by corresponding Cm, then this is always less than or equal to integral mod f minus Sn square. Okay, if you replace this gamma m by Cm, then Tn changes to this Sn. Okay, so this is the minimum value. At that case, we have if you put Tn is equal to if you put gamma m is equal to Cm, then we obtained integral a to b mod Sn of x square dx. Okay, what is this? This quantity is nothing but summation n equal to 1 to m is equal to 1 to n mod Cm square. That is already discussed. We have discussed that this integral mod Tn square is summation gamma m square. So if you replace Tn by Sn, then you can get this is Cm square. Okay, so this is same as this one, and we know that if you put gamma m is equal to Cm, from this you can write this mod f square. If we replace that, then you can get integral mod f square. So we replace this by I'll write integral a to b mod f of x whole square dx. That is because when you substitute gamma m is equal to Cm in this, then left hand side will be integral mod f minus Sn square. That quantity is always greater than or equal to 0. Okay, so and this quantity will be 0 by putting gamma m is equal to Cm. Then you can transpose this minus summation mod Cm square to the left hand side, so that quantity is less than or equal to mod f whole square. That is, this is integral a to b mod f of x whole square. Okay, so you can get this inequality. Okay, so this is always less than or equal to this one. Okay, that is the consequence of this theorem. Using this theorem, we can easily prove the theorem 8.12. We have another theorem that is the consequence of this. If sequence phi n is orthonormal on AB, this is an orthonormal system, and if f of x is the Fourier series of f of x is n equal to 1 to infinity Cn phi n of x, then we have summation n equal to 1 to infinity mod Cn square less than or equal to integral a to b mod f of x square dx. Okay, what is the meaning of this? If we take any orthonormal system of functions and we define the Fourier series corresponding to that orthonormal system for this f of x, integrable function f of x, then we have this result. Okay, that means the Fourier coefficients of the function f, the series of Fourier coefficients converges. That is the meaning of this. It's a square is convergent, that means it is absolutely convergent as well. So how to prove this? This can be proved using this argument. We have already proved that. For the proof, we take this inequality summation m is equal to 1 to n mod Cm square less than or equal to integral a to b mod f of x square dx. Okay, by letting n tends to infinity on both sides. Okay, so this will be summation m is equal to 1 to infinity mod Cm square. Okay, when by letting n tends to infinity on the left side, right side is independent of this n, then that will retains f of x whole square dx. Okay, which shows that this series converges. Okay, so the series of Fourier coefficients, okay, is absolutely square of this is absolutely convergent. Therefore, this implies the nth term tends to 0. Mod Cm square tends to 0 because this converges. Okay, and if this tends to 0, then we can get a limit n tends to infinity Cn tends to 0. Okay, so limit n tends to infinity Cn is equal to 0. That means whenever mod Cm square tends to 0 means mod Cm tends to 0 as n tends to infinity. Therefore, limit n tends to infinity Cn is nothing but 0. So this is the theorem 8.12. That is a mere consequence of theorem 8.11. Okay. Okay, now we consider trigonometric series again. So this was the motivation to define the Fourier series. So using that motivation, we have defined Fourier series for an integrable function f for corresponding to an arbitrary orthonormal system of functions. And now from now on we shall deal only with the trigonometric system. We shall consider functions f that have period 2 pi and that are Riemann integrable on minus pi to pi. So these are the only consideration from now onwards. Okay, then the Fourier series. So if you are considering trigonometric system, the Fourier series f is defined or Fourier coefficient is defined as earlier, and we write the Fourier series of this f is nothing but we write f of x, the Fourier series of f of x as summation minus infinity to infinity cn e power I n x. Okay, so this is the Fourier series of f of x. So now onwards we are dealing with only this orthonormal system of functions. Okay, so corresponding to the sequence of partial sum of this Fourier series is denoted as Sn of x. Okay, so this Sn of x or Sn f of x. Okay, so these are two notations to denote this sequence of partial sum of this Fourier series. So that is nothing but summation minus n to n c n e power I n x. Okay, so this is the sequence of partial sum of Fourier series. Our intention is to get the convergence of this sequence of partial sums. Okay, so if you recall the inequality what we have discussed in the previous theorem, we have 1 by 2 pi integral minus pi to pi mod Sn of x whole square dx equal to summation minus n to n mod cn square, and we have seen that this is always less than or equal to 1 by 2 pi integral minus pi to pi mod f of x whole square, that we have proved in the previous theorem. This is dx. Now our next intention is to find out the Dirichlet kernel for this Sn, or to get a better expression for this Sn. Okay, so this is not so handy notation or expression for this Sn of x. So next we will find out a convenient expression for this Sn of x using Dirichlet kernel. Okay, so first of all we define Dirichlet kernel. So this is this is denoted by dn. Using this dn we can get a better expression for this Sn of x that can be used to prove further theorems. Okay, so this is summation this is defined as summation minus n to n e power I n x. Okay, this is the kernel. So how will you simplify this? This is in fact e power I minus nx plus e power I minus n plus 1 x plus etc. plus as n is equal to 1 we have e power n is equal to 0 we have e power I 0 x plus e power I x plus etc. e power I nx. So these are the terms. So we can consider this is a GP containing 2n plus 1 number of elements with the common ratio as e power ix. Okay, so now you write the formula for sum of n 2n plus 1 terms of this GP with starting with this one, then you can get an expression for this as. So using GP you can write this as first term, that is e power I minus n into x into r raised to n. It contains 2n plus 1 terms and r is e power ix. So e power ix raised to 2n plus 1, that is e power ix 2n plus, this is capital N, 2 capital N plus 1 minus 1 divided by r minus 1, that is e power ix minus 1. Okay, so this is the sum, and we simplify this. You can get by multiplying this opening this bracket, you can write e power I minus n to n plus 1, so that is n plus 1 x minus e power I minus n x divided by e power I x minus 1. Okay, now multiplying numerator and denominator by e power I x by 2, e power minus I x by 2 on both denominator and numerator, you can get by multiplying this, you can get this will be e power I n plus half x minus e power I minus n minus half, that is minus of n plus half x divided by we have here, by multiplying the numerator we can get e power I x by 2 minus e power minus I x by 2. Okay, so this we can replace this to the sine function. This is e raised to ix minus e raised to minus ix, so that is sine n plus half x by 2i, and denominator will be sine x by 2 by 2i, so you can cancel 2i, then this becomes sine n plus half x divided by sine x by 2. So this is the Dirichlet kernel dn of x. So using this dn of x, we can get a better expression for our Sn of x. That is, if you write from this, you can write e power I x minus 1 times dn of x, that is same as e power before that we write Sn f of x. We need to get the better expression for Sn rather than dn, so we write Sn of x, that is summation minus n to n 1 by 2 pi integral minus pi to pi f of t e power minus int dt, okay, into e power inx. Okay, this is the definition of Snf of x. Because this quantity can be replaced as Cn. Okay, so this is Cn. So Cn times e power inx is the Sn of x. Okay, so when you replace the value of Cn here, then Sn of x takes this form, and by simplifying this, you can write this is 1 by 2 pi integral minus pi to pi f of t summation minus n to n. You can take this or interchange the summation and integral minus n to n, this e power I n x minus t dt. Okay, now you can replace this quantity by quantity in terms of dn of x, so that is, this can be written as 1 by 2 pi integral minus pi to pi f of t. This is nothing but from our definition, this is dn. What is dn? dn is defined as this, then this can be written as dn of x minus t dt. Okay, so this can be written as, because this quantity is nothing but our dn of x minus t, so now we can write this as 1 by 2 pi integral minus pi to pi f of x minus t dn of t. Okay, so this can be done using the fact that this dn is a 2 pi periodic function, because it contains only this e power inx, and by substituting for this quantity, okay, x minus t, then you will get a better expression for Snf of x. So these two quantities, the expression for Sn of x and expression for dnx, can be used to prove the next theorems. Okay, so in the next class we will discuss theorem 8.4, 14, 15 and 16. Okay, thank you.